Okay, so we're going to continue where we left off, trying to determine if this sequence converges. And remember, the way we know a sequence converges is if the limit as n goes to infinity of the explicit formula for the sequence, if that thing approaches some number. And if this limit approaches some number, that's like thinking about it as approaching a horizontal asymptote, then we say that the sequence converges to that value. And if it doesn't, then we say it diverges. Now in this case, if we do direct substitution and let infinity and n go to infinity, we see the numerator approaches infinity, and so does the denominator. So we get something of the form infinity over infinity, which we know is of indeterminate form, and so we can apply L'Hopital's rule. Now L'Hopital's rule works well when we have quotients, which we have here, so we can go ahead and just apply it. L'Hopital's rule says that this limit is equal to the limit as n goes to infinity of the derivative of the numerator over the derivative of the denominator. And as n goes to infinity, now the numerator goes to 0, the denominator stays 1, and so the end result is 0. So we say that this sequence converges to 0. Okay, let's look at the next example. We're looking at the sequence, the nth root of n, which when I go to find the limit of that, I'm going to rewrite that as n to the 1 over n power. Now direct substitution would give me something, the base is growing to infinity, and the numerator is going to 1 over infinity, which is approaching 0. So this is indeterminate form. This is a new one we haven't seen before. This is how I think about why it's indeterminate form. If we had infinity raised to some number, we know that that would be infinity, right? You raise infinity to any power, it's certainly going to be infinity. But if you have any number and you raise it to the 0 power, and when I say numbers here, I mean real numbers. So any real number to the 0 power we know is 1. So these two things don't agree. So this is why we call this indeterminate form. Now, we want to apply L'Hopital's rule, but it's not a quotient, right? So we're going to need to use our sort of natural log trick here in order to get this exponent down. So I'm going to set this thing equal to y, and the goal will be to solve for y. So we take the natural log of both sides, and now we have this property of exponents, of logarithms, that I'll write like this. So the, the natural log of x to a power is equal to m times the natural log of that x. And so we're going to apply that here, where here our x is n and our m is 1 over n. I'm sorry, I have one other thing to say, right? We need to be able to switch the order of this, which we talked about in class being okay. We're allowed to switch the order of those two. And so this is really just the natural log of n to the 1 over n. Okay, now I can go ahead and pull down my exponent. So I have the natural log of y is equal to the limit as n goes to infinity of 1 over n times natural log of n. Now, this is a product, right? So we've turned an exponent into a product, and we want it to be written as a quotient. But as we talked about in class, any product can be rewritten as a quotient. In fact, this one, I don't even need to think about it as multiplying by the reciprocal. I have it sort of already written. Look, if we could see this already written as a product of fractions, right? 1 times natural log of n over n times 1. So let me move over here. The natural log of y is equal to the limit as n goes to infinity of natural log of n over n. So in fact, this is a limit we've already seen, right? This is right here, that now we see that this is of indeterminate form, infinity over infinity. We finally can apply L'Hopital's rule the way we wanted to all along. And so we get the derivative of the numerator over the derivative of the denominator. So on the right, as we saw before, we get 0, and on the left we have the natural log of y. So to solve for y, we want to do the inverse operation of natural log. So that is to take e to the both sides of the equation. On the left, that gives us just y, and on the right we get e to the 0, which is 1. So finally we could say that our sequence C sub n converges to 1. Now, the next problem is actually very similar, except they're saying let x be some fixed number, some constant, right? So we want to think about x as if it were like a real number. So if I were to take the limit as n goes to infinity of x to the 1 over n, I'm thinking about this as some number being raised to the approaching 0 power. So this is going to give me just 1 directly, and I don't have to worry about going through the whole natural log trick. So in here we say the sequence B sub n converges to 1. All right, let's keep going. This next one asks us, does the sequence C sub n equals 3 plus the negative 1 to the n, does this converge or diverge? This is a sequence we looked at already, right? If we look at the first few terms, when the term number n is odd, then we're going to get 3 plus negative 1, so that's 2. And when the term number is even, this is going to be a positive 1, so we're going to get 4. So this thing's going to just alternate back and forth between 2 and 4, right? So this thing diverges, because if you think about it in terms of limits, the limit as n goes to infinity of this expression, this is going to equal either 2 or 4. 2 if n is odd, and 4 if n is even. So we didn't get a single limit, right? In order for us to say that this thing converges, this has to equal some single limit, and it doesn't. It equals two different values. Now next in the notes we'll see we have some properties of limits of sequences. And so these are just some properties that should make sense. If you have two sequences and you add them up, then if if the first sequence converges to A and the second sequence converges to B, then certainly the sum of them is going to converge to the sum, A plus B. So I think most of these should seem pretty straightforward. There is a little thing you have to be careful about. So the converse of this, of some of these theorems are not necessarily true. So say, for example, if you have the sum of two sequences and the sum converges, that doesn't necessarily mean that each of the individual ones converge. So here's an example. The sequence just n would converge. I'm sorry, would diverge because it's going to infinity. The limit as n goes to infinity, right? So let's think about, let me write something here. The limit as n goes to infinity of just n, that would go to infinity. And if my sequence is just negative n, that would certainly also converge because that's going to go to negative infinity. But the sum is 0, the sequence 0. That would just be 0, 0, 0, which also converges. So just because each of the individual ones diverge doesn't mean the sum won't converge. Okay, and then as it says, note that also some of the above properties are limits that you might have seen already. Okay, we're going to save the rest of the stuff for another video.